generalized scalar geometry, there's a very unusual situation that the complex structure of scalar geometry splits into two different complex structures, each of which is holomorphic Poisson. And that these holomorphic Poisson structures are not necessarily isomorphic. However, they are related by this holomorphic symplectic space, which is an analog of like the twisted cotangent bundle. Okay, but it's somehow different. And so if you ignore this green line, right, then everything else is purely holomorphic. And you should think of that as being the analog of, you know how in scalar geometry there's a separation of the degrees of freedom into the holomorphic degrees of freedom, and then there's the metric, right? So you usually think of it as, you usually, you know, if you were trying to study the moduli space of scalar manifolds, you would have two parts to it. One part would be the complex moduli, and the other part would be the moduli of the metric, which is infinite dimensional, because you could always add dd bar of a function. So similarly here, so this diagram is a diagram in the holomorphic Poisson category, and then the metric moduli is this C infinity cross section, which is Lagrangian for the imaginary part of the symplectic form omega. So here we have we have a holomorphic symplectic form on the whole space, and the imaginary part must restrict to 0. So L is an imaginary Lagrangian. Okay, I explained very briefly that the presence of this cross section is precisely what identifies the underlying smooth spaces where you have the complex structures. So if we didn't have this cross section, it's quite possible that this Poisson manifold and this Poisson manifold could be quite different. Remember in the first talk when we saw that two spaces could be Morita, two groupoids could be Morita equivalent, and the bases could be very different. Okay, that's what could happen for Poisson manifolds. Two Poisson manifolds could be very different, non-isomorphic, but they could be related by Morita equivalent. Okay, so that's the case here. But because we have this cross-section, we get this diffeomorphism between these two spaces. Okay, and then the interesting thing that happens is that you see this is a complex manifold, and these two foliations, the red foliation and the blue foliation, which are the fibers of these two maps, are holomorphic foliations, genuine holomorphic foliations. Okay? And so when you have a cross-section of a holomorphic foliation, what happens is that it gets an induced complex structure, right? Because this cross-section, right, can be identified with the tangent space of the whole space modulo the tangent space of the leaf. And because the whole space is holomorphic and the leaf is holomorphic, that means the quotient inherits a complex structure. So L inherits a complex structure from the quotient via the red foliation. But it also inherits a different complex structure because there's a different foliation passing through it, right? Now, normally this doesn't happen because normally in a complex manifold, we would consider a complex submanifold, a holomorphic cross-section. If this were a holomorphic cross-section, then the complex structure that's induced by these two foliations would agree. But because this is not holomorphic, it turns out that we get two different complex structures induced on the space. So this is the mechanism by which you get a pair of apparently unrelated complex structures, I plus and I minus. Okay, and then the final part of the data is that if we restrict the holomorphic symplectic form to L, well, the imaginary part must vanish because it's Lagrangian, but the real part may not vanish, and we get a real 2 form. And this real 2 form, we could extract a symmetric tensor out of it. And we could also extract it using the other complex structure. And these a priori would not be the same. They would be two different symmetric tensors. But because of the properties of this Morita equivalence, we get that they agree. What property is it that I'm talking about? The property is that the one that I mentioned before, which is that this foliation is symplectically orthogonal to this foliation. So this foliation is not Lagrangian or symplectic or anything in particular. It's just a foliation in a symplectic variety. And it will have a symplectic orthogonal foliation. Okay? And because these are symplectically orthogonal, these two symmetric tensors agree and give you the metric. That's how you extract the metric from this submanifold. So to be honest, it is a little bit unusual. I mean, I have never seen a geometric setup like this, where you get an induced metric on a submanifold without there having to be any metric in the ambient space. Right? It is quite striking that there is no metric except along this C infinity submanifold, a submanifold of something that is totally holomorphic. Anyway, it's food for thought, maybe. Okay, so why is this? Well, okay, so I mentioned, just roughly speaking, that once you see that a metric is given by a Lagrangian, then you can see that it's one scalar degree of freedom, because you can move a Lagrangian by deep derivative of a single function. But let's just make that more precise. So if you choose a Darboux chart, PQ, for the ambient holomorphic symplectic manifold, and this is a holomorphic Darboux chart, right, then this cross-section can be expressed as a 1-0 form on the base. So it would involve like DQs, DQI. Okay? So this is a cross-section. You could think of it you could think of the Darboux system as something like the holomorphic cotangent bundle of the Q space. Right? And on that holomorphic cotangent bundle of the Q space, we have a section, eta, 1-0. And the derivative of eta is indeed the holomorphic symplectic form restricted to L, and it's real. So this means that the imaginary part of eta must be closed. d eta is equal to 0 in the imaginary part. Because eta has imaginary part closed, it must be locally exact. dk for some real function k. And so therefore we can write eta as the derivative del of k. And the derivative of eta, which remember was the real part of the symplectic form, is just the derivative of this, which is d bar k. Okay? So we recover something like what you're used to in Kähler geometry, which is that the tensor which determines the metric, namely the symplectic form, is d bar of a function. Okay? But the problem is that this is not happening on the base manifold. It's happening on this auxiliary space. That's the difference. So this means that locally speaking, the metric is determined by a real smooth function, which is the generalized Kähler potential. That is our definition for the generalized Kähler potential, and it depends very strongly on the choice of the holomorphic Darboux chart. And the good thing is that it's a holomorphic Darboux chart. So it's part of the holomorphic substructure. It's part of the holomorphic moduli. Okay, so you choose that, and then you express your cross-section in terms of a single function. Let's do an example.
Sorry?
Oh, yeah.
That means this relation with K is just 2 on the chart? Or
Say it again.
so this relation is just 2 on U, or you can lift it on the wall?
This is, this slide, okay, what it's doing is it's giving a local description of what this Lagrangian is. That's all.
Okay.
The real global thing is the Lagrangian. That's what we learned from Donaldson, is that the Kähler potential is just a local description of that. So why do you not need to choose this PQ in the case of Kähler geometry? The reason is that in Kähler geometry, this space is the cotangent bundle. And so it's unnecessary to choose Darboux coordinates since it's already the cotangent bundle.
And why is eta 1-0 form? Because it was just a C infinity.
Because this is a holomorphic Darboux chart. Mm-hmm. So a holomorphic Darboux chart is like a holomorphic cotangent bundle. Mm-hmm. P's and Q's are holomorphic. So that means that P would be a function of Q, but the P's are just the holomorphic variables. So it's only a 1-0 form. Mm-hmm. That's the reason.
But L was any C infinity.
That's true. But a 1-0 form doesn't have to be holomorphic. It's smooth. Yeah. It's just of type 1-0.
Okay, I see.
Okay, so let's do an example. Let's take the C2. Let's take C2, okay, with a Poisson structure. The coordinates are x and y. The Poisson structure is x del x, y del y. And I multiply by t just to show you how it varies with t so that we can let t go to 0 and see what happens. Okay. Then the space z is double the dimension, x, y, a, b. Okay. And the source of this arrow, okay, is basically x and y, but x has been now acted upon. You act on x by the exponential of b times y, okay, with a t there. And the target is acting in the same way, but on the other variable. Okay, so you have this, these arrows are, when you turn on A and B, so if A and B are non-zero, so when you move up in the AB direction, what happens is that you start getting an arrow that goes from, from a scaled xy, where x is scaled, to another point where y is scaled. And the higher A and B are, the bigger A and B are, the longer that arrow is. Okay? And then the symplectic form, the holomorphic symplectic form on Z, has this expression, very simple, dA dx plus dB dy. So you see that this looks very much like a holomorphic cotangent bundle. This looks exactly like the cotangent bundle of C2. But the maps that go from C2 down to C are very different. They're deformed. They're not just a projection to xy. So if we let t go to 0, this is just the cotangent bundle of C2, the holomorphic cotangent bundle of C2. Now that we have our Darboux, well, okay, and we're very lucky because then we're already in a Darboux chart. So that means that all we need to do is to choose a smooth real-valued function of x and y. You pick a smooth real-valued function of x and y, and you're done. You can take this, for example. You can take let's say that you were on P1 cross P1. You could take this function, which is the typical Kähler potential that we know for P1 cross P1. Or if you were on CP2, you could take this function, which is the typical Kähler potential on CP2. So I'm just picking the usual Kähler potential, but that's irrelevant. I could pick any smooth function, right? And then I use this structure, and I will get a GK metric, just by taking this derivative. Take this derivative, dd bar k. We're going to get a function, we're going to get a two-form f, and then you take the 1 part with respect to I plus, multiply with I plus, and then a metric. And this metric will be very much different from the Kähler metric that we know on P1 cross P1. So this is how we produce the first, the first non-trivial generalized Kähler structures on CP2. They were constructed by Hitchin, and this is exactly. So he produced it by the flow construction, which you would have to integrate that real vector field that we saw yesterday. But instead of doing that, you can just pick this function, take derivatives, and you're done. So it's a much simpler way of coming up with examples of these backgrounds. Another example, so this one is a different Poisson structure. It's x del x, wedge del y, so it doesn't degenerate on y equals 0. It turns out that you can define, again, the space, the z space is C2 cross C2. We have these additional variables a and b. Now the source is just the projection, but the target is different. We rescale x and we translate y. And the holomorphic symplectic form on this space is given like this, which I wrote in a Darboux form already. Okay, so these are the peaks. A and B, they play the role of momenta. And then these combinations play the role of the positions. And then you can pick any smooth function, but I'm giving a specific example which has nice properties. So you can take the norm squared of Q1, and you can take the norm squared of Q2, but you envelop it in the dilogarithm function. Why do I do that? This is just a convenient, it's the most obvious choice. in order to get a complete metric on C2. So this happens to give a very simple example of a complete generalized scalar metric on C2. The two complex structures are different. Why does the dilogarithm appear? I have no idea. It's just the most obvious choice if you want to get completeness of the metric. Okay, so that I just wanted to demonstrate, how you would actually implement this procedure and get, use a function to generate one of these metrics. This was, let's say, this was what the aim of the series of physics papers by Rocek and Hall and Lindström and Zabdin. That's what they were aiming to do. They wanted to get a description like this where they could generate the metric out of a single function. And of course, they were driven to desire this. They thought that this should exist because of this n equals 2, 2 supersymmetry. So, it's another one of these cases where, because you know the supersymmetric model, and if you understand what it means from a physics point of view, you can you can predict, or you can guide mathematicians like me into what to look for. What should I do? That's what I do. Okay, so any questions about that? Because I'm going to move on to an application of this whole idea. So far, what I've explained is that the GK structures, despite the fact that the target of the sigma model is this Riemannian manifold with a schizophrenic Kähler structure, it seems to be very important to lift everything to this Z space, which is holomorphic symplectic, and which has this Lagrangian. And what I'm going to do now is I'm going to exploit this thing and try to actually, understand what the consequences of that are.
In the sigma model, do you also enlarge the target space and introduce new constraints implementing L maybe or something?
That is why I am here in Geneva.
Okay.
For 3 months to work with Pavel on this project. Yeah, we have many to do on this topic. Okay, so let's see. We're going to see something close to what you said in the rest of the talk today. So this is a summary of what I'm going to explain today. So we have a generalized Kähler metric. I explained already that this can be expressed as a Lagrangian inside this holomorphic symplectic manifold. Okay. Now, there's a notion of pre-quantization, which I'll explain, where the real part of this symplectic form is pre-quantized. And I call that ZCC. I'll explain why. And now, on the imaginary, this is representing the imaginary part of Z. This is a real symplectic manifold. And this real symplectic manifold has 2 structures on it. One is the Lagrangian, and the other is this pre-quantized real part, okay, which we will call a coisotropic brane. Okay, so this symplectic manifold has 2 branes on it. And I'll explain what I mean by that. And because it has 2 branes, we can exploit the A model of this symplectic structure, a topological 2-dimensional model, use boundary conditions L and Z, okay, and then take homomorphisms, right, in the A model to get a Hilbert space. I won't describe the Hilbert space structure, but I will describe the vector space structure. So I get a vector space. That is the proposed quantization of a GK manifold. That's the main point of today. But the second point is that this thing is a groupoid. And because it's a groupoid, these branes, the groupoid has like a multiplicative structure. So if I have a brane, I can convolve the brane with itself multiple times. And so we can do that. We can convolve the brane with itself and convolve this brane with itself. And in this way, we get a sequence of vector spaces. This is analogous to, when you take, we take a symplectic form and we pre-quantize it like this. And then we take the Hilbert space would be H0 of U. If we choose geometric quantization is telling us that we get a Hilbert space, which is the holomorphic sections of U. But then you could also take U tensor power to the K, and we could take the sum of H0, and this produces a complex algebra, a graded algebra, which is known as the homogeneous coordinate ring of the projective variety. Let's say if it was a compact symplectic manifold. This is the pre-quantization, and plus I want a complex polarization. Okay, you all have seen this. We get an algebra. Okay, so this is like each one of these is the quantization of k times omega. So we increase the symplectic form, we multiply it by k, we get a sequence of symplectic manifolds. We quantize each one of them, and then they all fit together into this system, this multiplicative system, which produces an algebra. And this algebra is, the fundamental part of algebraic geometry. You go between the complex manifold and the coordinate ring. And so the outcome is that we should expect to get a graded non-commutative algebra in this case, because there is no reason when you are taking these convolutions, because of the way the groupoid is, the groupoid doesn't, there's no reason why this should be commutative, and indeed it isn't in the few examples that we're able to compute. So this is kind of a partially realized dream at this point. I cannot say that we get a graded non-commutative algebra for every GK manifold. That's far from possible right now. However, there are some cases where we can implement this and we get the algebra. Okay, so let's see. And I wanted to recommend my favorite paper on quantization. It's this paper, Brains and Quantization, by Gukov and Witten, where they I hope that some of you have seen this paper, but if you haven't, you should read at least the introduction. It's a very beautiful introduction of 7 pages, where they criticized ruthlessly all the previous work on quantization, and they explain why their method is the best, and I actually agree with them. But it's very well written, the introduction, and I recommend it to everyone. Okay, but their basic idea was that if you have a symplectic manifold and you're trying to quantize it, right, you're trying to produce a vector space. That vector space should come from some kind of a category, should be like homomorphisms in some category. And what they do is they exploit the topological A model to produce that vector space. So their idea is that they want to quantize by taking a detour into the two-dimensional topological A model and output the quantization from that. Presumably this is not the only way to, maybe this is not a universal method of quantization, but it seems to be quite a powerful idea. Okay, so for those who are not so familiar, let me just review this concept. So the idea of a brain, the A model is a two-dimensional topological model. You have a two-dimensional surface, you have a map into what? Into a target. But the target is not Riemannian, it's symplectic instead. And given such a map, you can pull back the symplectic form and integrate it. That's your action, and so we get the model. And this is obviously a topological model. But if the two-dimensional surface has boundary, this boundary has to be sent somewhere, and wherever it is sent, that needs to give a kind of boundary term to the action, and that boundary term is the holonomy of a connection along that boundary. So that means that the boundary condition, where does the boundary get sent? It must be sent to a submanifold. This is the idea. I'm just telling you the standards. It's like a children's story. So the boundary must be sent to a submanifold of the symplectic manifold. This is the symplectic manifold. We have a submanifold, C. We have our, let's say this is sigma. This is boundary of sigma. Sigma is going to be sent with this. And the boundary will lie on C. But on C, we need to have like an electromagnetism. We need to have a unitary line bundle with connection defined only on C. And it must be such that we can, and so because of that, we can take the holonomy along the boundary, and that holonomy provides us a boundary term in the action. And actually, it's only well defined at the level of the exponentiated action, but that's okay. And the picture that you would normally draw is a picture of the two-dimensional surface with boundary, right? And the boundary must be decorated by this submanifold and by this line bundle. And this decoration I indicated by this color. And if we do that, then that's, in a sense, the domain of the quantum field theory. That's the data that you need in order to get, actual expectation values and actual numbers out of the quantum field theory. So the quantum field theory is a functor from the Bordisms of two-dimensional manifolds, Bordisms of one-dimensional manifolds, to vector spaces. And for closed a model where the boundary is a circle, right, this vector space is known as the quantum cohomology of the symplectic manifold. And we get a commutative Frobenius algebra because of this diagram. This diagram tells us that we get a multiplication on that vector space. But if we allow the boundary to be an interval, right, if we allow this to be an open string, that has to be labeled by a boundary condition. So this is now going to be strings that begin on C1 and end on C2. Right? Then we have this picture instead. And what it means is that from the tensor product of these two vector spaces, which are different because the decorations are different now, you get a product to this one. Now this can no longer be thought of as an algebra structure because these vector spaces are different. So instead, we view it as a category. We say that the vector space associated to this type of boundary with decorations C1 and C2, we define that vector space to be the Hom of C1 to C2 in a category that the quantum field theory defines for you. So we have now these decorations are viewed as objects of the category, and that's why we say that branes, the boundary conditions, form a category. And so this category of the A model has a name. It's called the Fukaya category of the symplectic manifold. This is not exactly correct. I put an asterisk there. The reason is that the people who study the Fukaya category, they don't consider all possible boundary conditions. They consider only Lagrangian boundary conditions. Okay? Whereas in the physics theory, you should consider all supersymmetric boundary conditions. And there are more boundary conditions than just Lagrangian. It was discovered by Kapustin and Orlov in 2000 that there are branes in a symplectic manifold, and these branes do not have to be Lagrangian. This is the part where the child has already gone to sleep, and now we have to tell them the truth, or we talk about the truth, and we have to speak in quiet tones. So, okay, so what is a brane according to Kapustin and Orlov? It's a coisotropic submanifold. You know what a coisotropic is. I don't have to tell you. I drew it there in orange. It's a very large submanifold. It's bigger than Lagrangian. And it has a line bundle with unitary connection. And that unitary connection has a curvature. And there's a constraint on the curvature. This curvature must be basic with respect to the reduction, the symplectic reduction to this symplectic leaf space. So this thing must descend to the leaf space. I know the leaf space may not exist, it may not be smooth, whatever, but let's suppose that it exists just so that I can explain what the structure is. Suppose we have a symplectic reduction of this coisotropic, right? Then the curvature must descend, and then that curvature, together with the symplectic reduction, the symplectic form, must produce a complex structure. The combination of the symplectic form on the base of the symplectic reduction with f must square to -1. Another way of saying that is that, well, we have two basic forms. We have the symplectic form of M is basic. That's what symplectic reduction uses. The symplectic form reduces to a symplectic form on the base. But this two form, this additional two form, must also reduce. And together, these two forms must be holomorphic symplectic on the base. That's why I drew these yellow hatches, because it's like a Darboux system. So this is a holomorphic symplectic manifold. Consider how strange this is. You started with a real symplectic manifold, and you have a brane in it. Okay? And all of a sudden you get a holomorphic symplectic structure out of nowhere. Okay? But anyway, that's what a brain is. So they're not, let's say, they're not the most, they're not extremely plentiful, they're a little bit rare, but they do exist. Let me give some, oh, and in particular, this places a strong constraint on the dimension, right? Because if this is holomorphic symplectic, it has to have real dimension 4K. So that means that this coisotropic has a constraint on its dimension, which is, it can't be just any dimension. Anyway, this is the real truth about what brains are in the A model. Let me give some examples. So one example, of course, is, I didn't even put it in the box, I put it up there. This coisotropic could be Lagrangian. And in that case, the curvature must be 0. And so we get a flat line bundle on a Lagrangian submanifold. And this is what people working in Floer theory or in Fukaya category would tell you. They would say the brains are Lagrangians with flat local systems on them. Okay, but here's the new stuff. New meaning that it's 20 years old already, but it's still considered new. Anyway, here's another example where the coisotropic is the entire manifold. The entire manifold is coisotropic, and we would need the curvature of the line bundle plus the symplectic form times I to be holomorphic symplectic. And this would define, actually, the complex structure. So how can we find such a thing? Simplest way, if you have a hyperkähler manifold, then just take the holomorphic symplectic structure that you have on a hyperkähler manifold. If you can pre-quantize omega j, then we have a space-filling brain. So anytime you have a hyperkähler manifold, if you take one of the symplectic forms, if you can pre-quantize it, that will be a brain for one of the other symplectic forms. Okay. Another example is if you take a complex manifold and look at its cotangent bundle, okay, then you can take a trivial bundle on that cotangent bundle. Well, okay, sorry, I don't have to say all these details. The point is just that the holomorphic cotangent bundle is holomorphically symplectic. And that will have a real and an imaginary part. And the real part we can pre-quantize because we have a canonical one form. We multiply by I star. This is the complex rotation applied to the canonical one form. And this thing, if you look at the curvature of it, the curvature is exactly it's exactly the real part of the holomorphic symplectic form. So we get this complex symplectic form where the real part is pre-quantized. That's a brain in the imaginary part. So omega, we think of the cotangent bundle the cotangent bundle of a complex manifold is a holomorphic symplectic, but we forget the real part temporarily. That defines a real symplectic manifold. The A model of that has a brain given by the real part. Okay, so these are space-filling brains. These are the two extreme cases. This is the smallest kind of brain you could have, and this is the biggest kind of brain you could have. Here's an example. We saw this one already. You take the cotangent bundle of S2 with the standard symplectic form. Okay? But we assume that omega here is not the same as omega canonical. Omega is the Kähler form on S2. Okay? So if we take the Kähler form, and if we pre-quantize it in the usual sense, okay, then you could take this cotangent bundle of S2, and you could pull back the pre-quantization of the Kähler base. That gives you a line bundle on this cotangent bundle. And what we do is we pull back the connection, right, that gave rise to the Kähler form downstairs, and we add this correction from the cotangent bundle. And then it's exactly this thing, this line bundle with connection. This is a unitary connection. The curvature of this is given by the canonical real part plus the pullback of the symplectic form on the base. And then the imaginary part is the same as the cotangent bundle. So this is actually quite familiar. This is the twisted cotangent bundle. Here's the twist. We're twisting it by the Kähler form from the base. So this is sometimes called the magnetic deformation of the cotangent bundle, where you take a 2 form on the base and you pull it back and add it to the symplectic form. So this is an example where we have a space-filling brain. Okay, So, can you remind me about when I should stop?
About 15 past.
Okay, great. Okay, so let's look at what Gukov-Witten were proposing. So Gukov-Witten, this is how they want you to quantize a symplectic manifold. You take their symplectic manifold and you embed it into a holomorphic symplectic manifold. Okay? In such a way that when you take the holomorphic symplectic form and restrict it to M, we recover the symplectic form that you want to quantize. But they want this submanifold to be Lagrangian for the imaginary part. Sounds familiar. So this means that now what we could do is look at this larger manifold and consider the imaginary part. The imaginary part is a symplectic, real symplectic manifold, and it has an A model. Hopefully has an A model. And in that A model, we have two branes. We have a Lagrangian, and we have a space-filling brane because of the real part. So that's what they call the canonical coisotropic brane. I mean, most of the time it's not canonical, but in their case it was canonical, so that's fine. I'll just keep using the same notation. So this means that from a pre-quantized symplectic manifold plus a choice of embedding into a holomorphic symplectic manifold, which has certain properties, they're able to produce two branes in the A model. So that means that now they have transformed the problem of quantization into a problem of the A model, a topological quantum field theory. And then when you take the Hom between them, you get a Hilbert space. And they're not kidding about this. They really believe that this is the source of most geometric quantization.
What is the inner product there?
They explain there's some more structure on this. There has to be an anti-holomorphic involution on this thing, and that will induce this Hilbert space structure. They explain that in great detail, but since I'm not going to use it, I won't talk about it. Okay, so in the cotangent S2 case, we have the Lagrangian zero section. That's a nice Lagrangian brane inside the cotangent bundle. But from this Fubini-Studi form, we pre-quantized it and we pulled it back to the cotangent bundle, remember, and we increased the brane. And so in the A model, when you have these two objects in the category, there's a whole bunch of vector spaces you could consider. You could consider the Hom from L to L, the Hom from Z to Z, and the Hom from L to Z. And so if you work this out, you're going to get a vector space, which is the geometric quantization of the two-sphere. And on it will act two other vector spaces which have an algebra structure because this is homomorphism from a brane to itself. And so those can be composed, and we get an algebra structure. That algebra is just C. This is a simple case. So C acts on this, obviously. But the other one has Hom from Z to itself, and what you end up with is this quotient of the universal enveloping algebra of SL2C, which is the complexification of, it's related to the SU2, which acts on the two-sphere symmetries of the metric, and you need to set the quadratic Casimir to 1/4. This is what's called quantum Hamiltonian reduction, and you end up with a non-commutative algebra that's acting on this thing. So this is an example that is explained in the introduction to the Gukov-Witten paper, and not exactly in this way, but pretty similar. Okay, so now we get to our idea. So our idea was to use this in the GK case, obviously, because we did all this work of converting the GK metric into exactly this type of scenario. It's a holomorphic symplectic manifold, Morita equivalence, that has a brane bisection in it. And because this is holomorphic symplectic, we can look at the real part as a brane on the imaginary part. Okay, and that's what we did in this paper from last year. I'll explain that in detail. Okay, now the problem, again, there's something of a dream involved in this because you cannot take a book on Floer theory and learn how to take morphisms between a Lagrangian and a space-filling brane. That does not exist because people haven't defined it properly. Right? They've only defined homomorphisms from Lagrangians to Lagrangians. So we need to have some kind of proposal for how should we define morphisms from a Lagrangian to a space-filling brane. And what we do is this. We try to mimic what happens in real geometric quantization, and we upgrade it to holomorphic geometric quantization. We say that, okay, if you look at this space-filling brane, which is this unitary line bundle on the total space whose curvature is the real part of the holomorphic symplectic form, we want to pre-quantize not just this, but the entire thing. We want a holomorphic line bundle with a holomorphic connection whose holomorphic curvature is this. That is a very strong requirement, but in the examples that we worked out, we can do this. And in the T star S2 case, you can do this. So now we have a holomorphic pre-quantization of the space-filling brane. And now that we have a holomorphic pre-quantization, we can take a holomorphic Lagrangian polarization and look for holomorphic Bohr-Sommerfeld orbits. Okay? And so that's what we do. We look at a sum of flat sections of this holomorphic pre-quantization over the Bohr-Sommerfeld leaves, which intersect the other brane that we want to compute Homs between. Right? So here, if I just took a sum over all Bohr-Sommerfeld leaves, it would not involve the Lagrangian brane. So I'm just taking the Bohr-Sommerfeld leaves of the big one, and I'm intersecting those with the small brane. And I get a sum of these particular Bohr-Sommerfeld leaves. So it's, if you're familiar with geometric quantization, this is like a holomorphic version, and that's what we try to do. Okay, so and that's the quantization. This is supposed to be the quantization of a GK manifold. Okay, so that's the end of that discussion. But now what we want to do is we want to do this type of iteration. We want to take powers of this thing and get an algebra. So let me explain how that is done. So, the nice thing about our case, and this is something that doesn't appear in Gugov-Witten, is that the symplectic manifold of the imaginary part is actually a symplectic groupoid. And when you have a real symplectic groupoid, this is a real symplectic groupoid. Okay. Then remember that the multiplication, where does it go? It goes from the composable arrows to G. And the composable arrows are inside the product of G with G. That means that there is a relation from G cross G to G. Another way of saying it is that the graph of M sits inside G cross G, where these two, in order for this to be Lagrangian, I need to reverse, put a minus sign in front of the symplectic form of G. G, the two domain parts, and not on the other part. Okay. And so because of this, the interesting thing is that when you have a relation like this, a Lagrangian relation between two spaces, what it means is that if you have, let's say, a Lagrangian, let's say L1 cross L2, let's say you have a Lagrangian in G, and you have another Lagrangian in G, then you can take the product of these two Lagrangians, and that will be a Lagrangian in G cross G. Now, instead of thinking of it as a submanifold, you could think of it as a relation from a point to here, because it's sitting inside the product of a point with G cross G. It's a tautology. Okay? And then you could take this relation, which is Lagrangian, and you could compose it with this Lagrangian relation, and you would get another Lagrangian relation. And this would be called the convolution of the two Lagrangians in G, and we get a new Lagrangian in G. Okay? And so that's what we do. We take iterated convolution, and it turns out that this procedure also works for branes, general branes. It doesn't have to be Lagrangians inside G. It could be any brane. So we take our initial branes, Z and L, and we take the convolution with themselves, and we produce this sequence. And then we would like to take, so here I've chosen the Lagrangian. Don't be confused by, so here I should have L convolve to the K, but I'm considering L to be idempotent, so that L convolves with itself to be itself. Okay, but never mind. The point is that then we would be able to get an algebra by taking Hons between Z2 and L2, Z3 and L3, Z4 and L4, and so on. Okay, and so then, in order to do this, we need to use our proposal. We need to holomorphically prequantize and look at the Bohr-Sommerfeld leaves for this thing. There's an additional complication, which is that the prequantization of the brane Z must have a compatibility with the groupoid multiplication, so that when we want, if we want this convolution to work properly, this space-filling brane on this symplectic manifold, it must be compatible with the groupoid multiplication in order to be able to do this. And so for that, we need a specific multiplicative cocycle on G cross G, which implements that. I just wanted to point out that there is something non-trivial that we need from this space-filling brane. We need the space-filling brane to have this multiplicative cocycle. Okay, and I just wanted, in the last 5 minutes, to describe how we actually implemented this in a particular case. So what we did was we said, okay, take any toric variety. Take any toric variety and prequantize it and linearize it. So we want that the action of the torus should be defined on the line bundle, not just on the base. So we linearize the torus action so that it's acting on the prequantization. That's fairly easy. That's the same thing as choosing a moment map. Okay. And then we take the cotangent bundle of the toric variety, and we obtain a torus action there. The cool thing is that when you have the complex torus action on a toric variety, there's no moment map for that. There's only a moment map for the real part, for the real torus action. But if you look at the torus action, the complex torus action on the cotangent bundle, then everything becomes Hamiltonian on the cotangent bundle. And so that means that the complex torus action gives us a moment map on the cotangent bundle, which is a holomorphic moment map for a holomorphic action of C star to the K. So we get this momentum map. This is going to be important because we're going to use the fibers of this holomorphic moment map as our holomorphic Lagrangian polarization. That's what we're going to use this for. Okay, so far everything I said is just toric geometry, toric Kähler manifolds. Now I want to bring in generalized Kähler, and I want to turn on a holomorphic Poisson structure. So you choose an R matrix in the Lie algebra of the torus. You push it forward by the action, and we get a holomorphic Poisson structure on the toric manifold. So now we have a holomorphic Poisson structure on the toric variety, and there's plenty of these. You just take any, you could take any skew-symmetric tensor in the Lie algebra, and you get this holomorphic Poisson structure. And then you could also lift, by using the linearization, you could lift this to a Poisson structure on the line bundle as well. Okay. So it turns out that Weinstein and Shu, who were working intensively on groupoids for many years, they actually explained explicitly how to produce the groupoid of this type of R matrix Poisson structure. What you do is you just take the cotangent bundle. You take the cotangent bundle with its standard holomorphic symplectic form, but you modify the target and source maps by this very strange procedure. You say that if you have a point in the cotangent bundle, think of it as an arrow now, okay, whose source is not the projection down to the base as usual, but it's that with an action of a Lie algebra element exponentiated for a certain amount of time. Which Lie algebra element is it? Well, you're supposed to take that point in the cotangent bundle, map it by the moment map to the dual of the Lie algebra. The dual of the Lie algebra contracts with the R matrix to get an element of the Lie algebra, and then you exponentiate that to an element of the torus, which acts on that point. So basically, you have to push the point down to the base, and then act by a certain element of the torus forward and backward. And that gives you the source and the target of the arrow. So it gives you a non-trivial groupoid structure on the cotangent bundle. This is what Ping Shu wrote in great detail and studied its properties. And the prequantization is exactly the same as the prequantization in the Kähler case. The prequantization line bundle is no different from the way it was in the Kähler case, where this R matrix is set to 0. The only difference is that the cocycle has to be modified. The cocycle involves the R matrix evaluated on the image under the complex moment map of the 2 points that you are, the 2 composable arrows. So we get this very nice cocycle, and we are able to we're able to produce a we're able to proceed with the production of the algebra. Okay, so in order to compute the algebra, we need to find these holomorphic Bohr-Sommerfeld leaves. So it turns out that the Bohr-Sommerfeld leaves are exactly in one-to-one correspondence with the integer lattice points in the dual of the real Lie algebra. So we have, let's say for CP2, we have this moment map into R2. We have all these integer lattice points in the image of the moment map. And all of these are Bohr-Sommerfeld leaves, all of them. There's an infinite number of them. But if you look at the Bohr-Sommerfeld leaves that actually intersect the 0 section of the cotangent bundle, it turns out to be exactly those which lie inside the moment polytope. And so that means that when you end up with this integer lattice points in the Delzant polytope for k times omega, so the ones that intersect, when you convolve the space-filling brane with itself multiple times, what happens is that the size of the triangle gets larger and larger, and the number of these lattice points that you should actually include into the kth part of the algebra increases with k. And then we verified that when you take this product of sections, so the Bohr-Sommerfeld leaves, when you take flat sections along them, it coincides with this vector space. And when you take the product that is induced by this in the algebra, we get this commutation relation. F star g is not equal to g star f, but it's modified by exponential of the R matrix, like this, which is depending on the weights of f and g. So f and g have certain weights. I'm choosing a basis here for the functions on CP2, which are corresponding to these integer lattice points. These are the monomials. The monomials have certain weights. You plug the weights into the R matrix, and you get your factor. So what does this look like? It looks like the non-commutative torus. It's just the non-commutative torus, but it's a compactification of it. So the point is that CP2 is a toric variety. It contains a torus, C star and C star. The R matrix C gives a non-commutative torus structure on C star cross C star, but this procedure, compactifies this thing to CP2, and we get something like a non-commutative torus algebra, but on this vector space. This vector space is just the usual homogeneous coordinate ring of CP2, and so we end up with a non-commutative algebraic, deformation of the usual homogeneous coordinate ring of algebraic geometry. Okay, I'll leave it there. Thank you for your attention.
Are there any questions?
So if you have a real analytic symplectic manifold, I suppose that you can go to some complex neighborhood and do this holomorphic structure. Is
That's
that
what they
enough?
suggest in their paper. What they say is that in order to, at that time, their idea was if you have an analytic real symplectic manifold, you should complexify it. And so for them, this Z space was always the complexification. And so they were limited to using this idea in a case where it was possible to find this complexification of the symplectic manifold. The problem, though, for them is that they need the A model to be defined on that holomorphic symplectic manifold. If it's just a small neighborhood, the A model is not going to be defined there. Well, they believe, I mean, there's a question about like, how do you define the A model in a non-compact space? They prefer that, what Witten told me is that it's impossible for me to tell you when on a given non-compact space the A model would be defined. However, if it is a complete Riemannian, if it's a complete hyperkähler manifold, then he's sure that the A model will be defined, right? And then, of course, we have in mathematics, we have cases where the Fukaya category is defined on a non-compact space, and those, again, they tend to be complete in the sense that when you take functions and look at their Hamiltonian flows, they're complete, and this complexification would not, unless it really was somehow complete.
So in geometric quantization, a complex structure gives some kind of special polarization, but can you do this for something similar for other polarizations, or is it?
Yeah, that's a good point. So because we're doing like a holomorphic version of geometric quantization, the only one that really makes sense is the real polarization. It becomes like a foliation of holomorphic Lagrangians. It's unclear what another type of polarization would be. I prefer to just stick with the holomorphic Lagrangian polarization for now. But yeah, it's some people have speculated that maybe having a hyperkähler structure could be viewed as a polarization in a sense, but it's unclear.
So I got slightly confused. So this cocycle that you need, is it an extra structure, or how difficult to get it, or is it somewhat automatic in your setup? What's?
Yeah, this cocycle here.
Mm-hmm.
Right. So it's like it's part of the pre-quantization idea, right? So if you have a space-filling brane on the base, right. So if you have a space-filling brane on this groupoid, right, then there's a question. So first of all, you want to make sure, in order to be a brane, it has to be pre-quantized. So there's got to be a line bundle with a unitary connection whose curvature is that real part, which is the partner of omega naught. Okay, but if we want to use that space-filling brane to do something like this, we need to be able to we need that space-filling brane to be compatible with the groupoid multiplication. And so that's kind of like part of the pre-quantum data. And so there is an abstraction to that, and so you could express it in terms of groupoid cohomology. And we're lucky that in our chosen example, that exists and it's canonical, and you can build it from the R matrix. But it's not clear. Yeah, I mean, what you would suspect is that if you can't do this, if it's obstructed, then perhaps the geometric quantization is bound to fail. And maybe it explains partially why some classical cases of geometric quantization fail.
So this is a part of so this is the upgrade of pre-quantization.
Absolutely, yeah.
One more question. So when we were doing coisotropic manifolds for some manifolds with deformation quantization, it was discovered that you start from a coisotropic submanifold, and then you see that the condition of being coisotropic gets quantum correction. So you have to correct, you can deform your submanifold in order to remain quantum coisotropic, and sometimes there are obstructions. Right. Is there some similar story here?
I'm really not sure because you're speaking of the Poisson sigma model and about whether a coisotropic is a brane. And if you look at the supersymmetric branes in the paper of Kapustin and Orlov, they are very serious about the statement that the branes really are these coisotropic A-branes, and that there is no need to modify them, just like for Lagrangians. So they view them as being exactly on the same footing as usual Lagrangians with flat line bundles. And actually, just for your information, the reason that they found these coisotropic A-branes is because of mirror symmetry. They took the symplectic manifold, they saw that there was a dual B model on a complex manifold, and then they looked at the category of objects there, and they had all these other objects besides the ones that came from Lagrangians. So they just took them and transported them over, and they saw that there were these coisotropic branes. So in view of that, it's pretty clear that these things are for real. They're really supposed to be supersymmetric boundary conditions which are valid for the quantum theory. I don't know the details of your construction, but I suspect not, I suspect.
I have a question.
Very good.
Can you, at some point, describe, actually this slide, you take sum over something intersection of B at this Bohr-Sommerfeld leaves, and what is E?
Oh, I'm sorry, E is L, sorry.
No, okay.
I sometimes, it's a mistake.
So do these always intersect transversely?
Thankfully, in this example, they do. But no, they may not, in which case, yeah, we've got a problem. In principle, you should replace this intersection with the Floer intersection.
What happens if you take sum over all the orbits and you grade them by intersection multiplicity?
Sum over all the
the Bohr-Sommerfeld leaves, and you grade it by intersection multiplicity.
Oh, I mean, I don't know if it's so much that it's a intersection multiplicity. This intersection would really be two Lagrangian submanifolds intersecting in a symplectic manifold, and so we should really do the Floer complex,
I see.
right? And so that's the right way to account for the multiplicity and so on. And in principle, we should do a Hamiltonian deformation to make them transverse, and then sorry, I should have answered your question in a simpler way. If they don't intersect properly, then according to Floer theory, you should be able to take one of them, Hamiltonianly flow it, okay, and until it is transverse, and then take the Floer intersection.
So it is some over like Homs in some Fukaya category?
Correct. Absolutely, yeah. The way that I usually explain this is that this Bohr-Sommerfeld, what it does is it takes your coisotropic brane and it dissolves it, or it crystallizes it into a bunch of Lagrangians. And then you can use those Lagrangians in the Floer theory that we have on the shelf and try to use those to make the Homs.
So those may be like continuously many.
Continuously?
Continuously many. They may be like
In principle, you mean how many Bohr-Sommerfelds there are?
Yeah, I do have like
Continuously many, but in this example, there were discrete, and so.
I suggest we postpone all the question to lunch.
Then let's thank Marco.
Thank you, and thank you.